So the mission for this week is just basically to continue, and I'm going to go a bit deeper into some of these circuits that we just talked about last time. No real new circuits, but I want to tell you a bit more about how the retina works. And in the form of this particular product, the first product that we ever sold is called the Physiologist Friendship. And then after that, I'm going to tell you about some cool circuit techniques like the cascode. I'll talk again about the Miller effect, and then we'll go into some deeper analysis of the second order behavior of this photoreceptor circuit that you guys are doing simulations and small signal analysis of. So that's the plan. And so I'm going to talk a bit about this, photoreceptor cell itself, this fascinating biophysical photoreceptor cell, but in the context of making it adaptive, making it actually have a kind of a high pass frequency response. And then in the context of this particular chip called the Physiologist Friendship. And in the past, we always taught about this adaptive photoreceptor. Does this circuit look kind of familiar to you? It's the same as the circuit you tested, except for that red part right here, right? And what I'll try to explain to you in the context of the circuit that you tested so far is that this red part here acts like a kind of a feedback circuit, which has decreased feedback at high frequency. See, at DC, this this resistor-like element is a short circuit. And so it's exactly the same circuit that you guys have simulated and we talked about. But for AC, for changes, the feedback goes through this capacitor divider. So for high frequencies, there's less feedback because it's divided down by this capacitor divider. Because there's less feedback, you get more forward gain. And so that's how you can get a response which has a steady state response like the biological receptor that's flat like this, and has a transient response like this that has high gain. And if you actually lay out a circuit like this, it's quite cool because it's not so, it sort of looks like what you expect, right? Here is the photodiode. In this case, in this particular case, we made the photodiode just by extending the source of this NFET. So it's just the N source drain region. This is looking down on the thing. Here's this transistor. Do you see where that transistor is? It's this one right here. That's the photodiode down there. And then the amplifier is these three transistors here. It's actually three of them because it's not two like this blue circuit here. It's three because there's a cascode here, a long cascode transistor. The green is the source drain or thin oxide region. And you see how it goes around like this? It snakes around, makes a really long cascode transistor. And then that feeds back through this resistor-like thing, which is a pseudo resistor. It's kind of a transistor arranged to be a very high resistance element. And then what's this over here? This is the two capacitors, right? The C1 and the C2. It's poly capacitors. And all this was built in the history of neuromorphic engineering to mimic things like the center surround computation that's happening in the biological retina. And this image is quite famous in the history of neuromorphic engineering because it's from the cover of Scientific American from Mishima Howell's PhD work. It's Silicon Sees a Cat. And she worked for hours and hours and hours to get her cat to stay still long enough or move just enough so she could get a nice picture of it for the cover of Scientific American. Okay. So I'm going to go through the basic three-layer retina circuit, which is photoreceptors plus bipolar cells plus horizontal cells, which leads to ganglion cells. And then I'll briefly talk about the biological photoreceptor in the context of this adaptive photoreceptor. And then I'll spend quite a lot on the blackboard discussing these, especially the speed up, the second order system analysis and stuff like that. There's a lot of chicken scratching, a lot of equation mangling to do with that. Okay, so here's the famous three-layer retina circuit, which is a model of how our eyes work. You remember this picture, right? From last time, how you have these layers of cells starting with photoreceptor, bipolar cells, ganglion cells. Those are the three layers: photoreceptor, bipolar, ganglion. Along the way, there's the horizontal cells and endocrine cells. And then they come out as spiking neurons going to the brain. The reality is that it looks more like this. I don't think I showed you guys this picture. This is a real biological cross-section of photoreceptors. See, they're actually quite small compared to all the other neural machinery that sits between the photoreceptors and the ganglion cells. These are the ganglion cell bodies. And then you can't see it here, but this gray matter is like the fibers going out along the along the eye towards the optic nerve. And this is the outer nuclear layer where the bipolar cell bodies are. And this is the inner nuclear layer where the amacrine cell bodies are. And then in between are these gray matter where all these dendrites. And it's really complicated. It's like 20 or 30 classes of cells in each layer that are doing all kinds of sophisticated calculations that people don't really understand yet. But the simplified model that captures a lot of what it does is captured in the silicon model of this physiologist friend. Why is it called physiologist friend? It's because this chip was meant to be a tool for neurophysiologists to calibrate their visual physiology setups. In other words, you could plug this chip right in front of the computer monitor that you would be showing the animal, and then you could show it the visual stimuli that you would show the animal. And then you could record neural responses from it and make sure that all your recording setup was working in your analysis software and all that kind of stuff. And so the way it works is it has a little retina of just 7 pixels arranged in this hexagonal way. These are photodiodes here. And then there are layers of circuits that mimic the photoreceptors, the bipolar horizontal cells, the ganglion simple cells, and there's even a couple of cortical cells on this chip, which are simple cells that have different orientation type responses. So they have receptive fields that are composed out of all 7 of these photodiodes. So how can you design such a circuit? You probably can almost design it yourself right now using the circuits that you've already learned in the class. But let's just do a little thought experiment. If you wanted to do that 3-layer retina, perhaps you could wire it up like this. You take your photodiodes, so you just do it as a line here to make it easier to draw it, right? This is actually done as a class chip project a long time ago in the class. And you want to do this center surround computation that the eye does, because we know that the horizontal cells are some spatial temporal average of what the photoreceptors are saying. And the job of the retina is to send on that high pass difference and to rectify it into on and off outputs, right? Brighter than the surrounding and darker than the surrounding. And so the circuits are arranged to do that. I mean, you have the photoreceptor circuits all connected to one horizontal cell. The horizontal cell computes the spatial temporal average. And then the bipolar cells take the kind of difference between the photoreceptor and the average, rectify it into on and off channels. And then the result is that you should get these center surround receptive fields, which is what you actually observe in the retina. So this cell responds when it sees bright surrounded by darkness, and this cell responds when it sees darkness surrounded by brightness. And that's the output of your eye. That's the basic operation, either in space or in time. And so you can see what Carver liked to call the organizing principles of the nervous system there. So you use physics to compute averages over space and time, and that finds a kind of a context, a spatial temporal context. And a second organizing principle that's expressed here is to represent sign quantities by rectifying into separate channels that typically have low activity. In the nervous system, you don't want to represent 0 by spending a lot of energy, because there's a lot of zeros, a lot of sparseness. And so you should represent 0 by doing nothing, and then split the negative and positive into separate channels. It's sensible, right? It's very different than a binary representation where representing 0 is the same cost as representing every other number. And the other thing is, this is an implementation of something that computes locally in analog and transmit long distances using digital spikes, which is how your mammalian brains are built. Any brain that's bigger than a millimeter or so uses spikes to send signals long range. Okay, so the photoreceptors and then the horizontal cells. Let's look at this horizontal cell. These are really cool. We talked about the photoreceptors before, but let's look at the horizontal cells. So if you actually go into the retina and inject one of these horizontal cells that's sitting just below the photoreceptor, if you inject it with something that stains the cells black, and that goes to other connected cells that are connected by gap junctions. And a gap junction is a very special kind of synapse that's actually an electrical connection directly between 2 synapses, different than a chemical synapse. A chemical synapse is more like a transistor, right? The chemical is released by the synapse, and then it causes a conductance on the other side. A gap junction synapse is actually a little tiny pore that's connecting the 2 cells electrically, because it let ions through. So if you fill this cell here with a stain, it actually goes to the connected cells, and you see they're actually connected in a hexagonal lattice. And these are these horizontal cells that are laterally connected across the retina. And their purpose is really like a kind of a resistive sheet. They compute the average in a neighborhood of maybe 3 or 4 cells, the space constant. Like the exponential space constant is like a few cells. And why do they do that? Because it makes sense, right? If you can avoid sending gray, that's good because you save a lot of energy. Because most of the world is not changing. So how do you actually implement this horizontal cell using the circuits that you know about? How can you implement a kind of a very simple model of this averaging circuit? Well, you know about transconductance amplifiers, right? Okay, so what if we do this? We take the photoreceptors and we hook each of them up to a follower integrator, just like you guys did, and then we wire up all the follower integrator outputs together. And this is called a follower aggregator, and it averages the photoreceptor outputs to compute the average of the inputs. This average is the context which is compared to the photoreceptor. Can you see why this computes the average of all these input voltages? It kind of makes sense, right? It's basically each one of these, the input current is the difference between this and this V average. And so if you just write down the expression for that, you'll see that V average must be the average of the photoreceptor inputs if it's linear. Do you want me to do that calculation for you? Or do you just kind of make sense?
It makes sense, but it would be better if we could see also the calculation itself.
Okay, so let's just do it. Let's suppose that it's linear. I need to now I need to turn on this. I'll do it on this whiteboard, on this on the whiteboard. It's just easier to draw. So let's say that we have V1, V2, and so on up to Vn, all hooked up by resistors. Let's suppose they're not transamps, they're just plain old resistors, and this is V average, we claim. Let's see if that's true, okay? So what's the current flowing into each one? And the sum of the currents must be 0. So the sum of Vk minus V average over R, and they're all the same R, right? For the moment, must equal to 0. No, I mean, the currents have to add up to 0, right? And so it doesn't matter what R is, we can just cross it out for now. I mean, it just sets the time constant if there's some capacitance here, right? But in steady state, so the sum of Vk plus N V average equals 0, minus, if there's N of them. Okay, so V average, now it's clear, right? V average must be a sum of Vk over N. Is it clear?
Yes, thank you.
Okay. Okay, so that's how you do the calculation. But of course, these circuits are not resistors. They're actually transconductance amplifiers. In this small signal region where Vk is almost the same as V average, then they act like resistors. I mean, the output current is just proportional to the difference of the input voltages, right? But in reality, what happens if the voltage difference is big? Then they saturate. And that has a very cool effect, it turns out. That's actually not so easy to compute numerically. Yeah. Yeah. Now imagine what happens if all these photoreceptor voltages are close to each other and one of them is many volts away. If this was a linear computation, then this one input that was a long ways away from the others would act like an outlier. And you know the problem with outliers, right? And linear statistics. One outlier can pull you way off. But what happens if that amplifier saturates? If that amplifier saturates, it limits the effects of any outliers. And if you work it out, you'll see because the follower input output current saturates, the follower aggregator computes the mean when the differences are small. And it turns out it actually computes the median of the inputs when the differences are big. And that's very cool because the median is a very nonlinear computation. In other words, it computes kind of the middle value, right? If you work it out just by counting. Anyway, I thought that's kind of cool. So keep that in mind if you ever need an analog median computation. You just need a saturating amplifier. Okay, so that's the horizontal cell. That computes the average for you. And then what about this bipolar cell? We somehow have to take this difference between the photoreceptor and this average and rectify it into on and off parts. How do we do that? You guys already tested the circuit with your own hands that can do that. Do you know what it is? Is it the diff pair? If I take a diff pair, is that going to do the diff? Is that going to rectify it into on and off or not? The diff pair, if you take a diff pair, right, and hook it up so that one input to the diff pair is the photoreceptor and the other input is the bipolar cell, then you'll get two outputs, right? I'll just draw it here. Do you see the laser pointer? I'll attempt to annotate here. Yeah, I'll attempt to annotate with this tool. Let me draw it in red here. I'm not sure if this is going to work. Yeah, okay. So if I take a diff pair with a current source on it and hook this up to the photoreceptor and hook this up to the horizontal cell, then is that going to give me an on and off difference that's zero when the difference is zero? No, it's not correct, right? Because a diff pair would do this. So the on. This is not terrible drawing. I can't erase. Let me undo this. Maybe I can backspace here. I can't erase. Okay, so the diff pair would give you something like this. Let me put this drawing thing over for us. I can get at it. So like this would be, let me draw the on in red. It's delta V here. This is I out. So that's one half, right? And the other half would be in green. It'd be like this. Okay. Is that what you want? No, because now when the difference is zero, you still have a big output. You don't want that, right? You want the difference, the output to be zero or close to zero when the difference is zero. So, but you did test a circuit that does have an output that's more like the rectifier. Do you remember which one? I mean, what you'd like is something that looks like this. Let me see if I can. Stop this drawing. Okay, this is actually showing the synapse. Before I go on, I just want to show you this absolutely beautiful. There's at the rod horizontal cell bipolar junction. This is the photoreceptor cone pedicle, which is wrapped around the rod bipolar and the horizontal cells. They all come together in this thing called a triad synapse. It's actually a synaptic connection that's optimized for very low noise and differential computation. At this synapse itself, the synapse itself takes this kind of difference between a photoreceptor, the horizontal cell, and bipolar and rectifies it. And do you see these little circles here? Do you know what they are? They are the vesicles of the neurotransmitter. So each one of these little vesicles, which is like a little ball of lipid monolayer containing the neurotransmitter, they're clustered up right next to the so-called ribbon synapse. And do you know why they're clustered up there? That's so that when the voltage changes on the synapse, they can be released very reliably. almost like lining up at the supermarket queue at Migros. So you're ready to go out. And so that's to reduce the noise in the transmission. Okay, but anyway, this thing does this kind of difference and rectification. So what you'd like is something like this, right? Not what I drew down here on the bottom right. You'd like something that really rectifies. So when the input is positive, you get on, and when it's negative, you get off. A little bit like a ReLU, you know, in a DNN. So how do you do that with a circuit? Do you guys know? Somebody knows the circuit here, I'm sure, because you guys tested it.
Wait, I don't think this is what we're looking for, but couldn't we use a winner-take-all circuit for this?
Where's the differential input? I suppose you could, but then it has an extremely sharp response, right? If you use a winner-take-all, I mean, it would just shoot up like this. Okay, so you tested it. I think when you did the static circuits, didn't you test it? It has 3 outputs or 4 out. It actually has 3 outputs. Right. This one. Do you guys remember testing this circuit? The bump circuit?
Yes.
Okay, so if you compare that, I'm going to erase this drawing here. That's stupid. Sorry, guys, I'm having trouble. This annotation tool. I had to locate it on my screen here. Where the hell is it? Oh, there it is. Okay. Clear it. Okay. Okay. Do you see the difference here? When the difference is 0, the output is low on and off, right? Because most of the current is flowing down the middle branch. But then when you get a negative or positive thing, you get the current going out the on or off output. Okay, so that's what you could use to rectify into on and off. And then finally, you've got to take those currents, those on and off currents, and make spikes out of them. You know how to do that, right? You just tested the neuron circuit, I think. Was it last week? So all you need to do is hook up a neuron. You don't need any of this fancy DPI, SIDAPs, and all that kind of stuff. All you need is take that current and send it straight into a neuron, a spiking neuron. In fact, you don't even need a fancy neuron like this current feedback neuron. Just use an axon Hillock circuit. There's something that takes current and makes spikes. It's a little bit like the C2F circuit. So let me clear this drawing here. Go back to this. Yeah. So take that current from the on and off and feed it into this axon Hillock circuit. By the way, for the purpose of the exam, was everybody straight on how this axon Hillock circuit worked? Did Giacomo explain it? And can you explain it yourself? This is important because we often ask about this on the exam, how this particular simple neuron circuit works.
Yeah, I think Giacomo went through it quite thoroughly.
He went through it, yeah, but you should understand how it works and be able to explain it, right? You have a capacitive divider here on the feedback loop. What happens is this voltage here on this VMEM charges up until it reaches the threshold of this comparator. Once it reaches the threshold of the comparator, which is V out goes high. And when V out goes high, that couples back through the capacitive divider and it lifts up VMEM. And the amount it lifts up VMEM is VDD times the cap divider ratio. So this input capacitor is charged up instantly, just following because the capacitor, right, it's instantaneous, charges up. And then this picture is not correct here, right? Because actually what happens is then the neuron starts discharging. V out is high, so this transistor turns on. You have some V pulse width control down here that limits the current. Then VMEM goes down until it reaches the threshold again. This picture is actually not correct. When VMEM reaches the threshold again, it goes low. Suddenly, the input to this comparator crosses the threshold. Now V out goes low. It charges down by VDD times the cap divider ratio, and then it has to charge back up again. And so, the neuron circuit is incredibly simple. I mean, it has a drawback that if this is a real inverter here, it burns a lot of power as you're crossing the threshold. So you have to use static inverters there, not the traditional inverter. Instead of using the inverter that looks like a digital inverter. Do you guys see the problem? So if you use a traditional digital inverter that looks like this, then of course, as this voltage here crosses half VDD, both of these paths are going to be on, and this thing's going to be burning many milliamps of current. That's a lot of power to burn just to slowly cross the threshold. And so instead of doing that, what you do in this circuit to reduce the power consumption is to use something like a static inverter. So you just put a static bias on one branch. And then, basically just an amplifier. And then the output is just like this. And now the power consumption is limited by the bias current that you put in the top transistor. And so you put a couple of those in series, and then you can kind of limit the power consumption. Of course, it also limits the slew rate, but then you can bound the power consumption. And by the way, this picture is wrong, right? There's no reason that it should switch when it gets to this point. This should actually switch when it gets here. And charges up again. And it switches down here again. And it should charge just the amount that it charges up here through the cap divider should be exactly the same as the amount that it charges down the other side. Any questions about that? Okay, so anyway, so here's your spiking neuron. Once you have that spiking neuron, you can you have the whole circuit, and here's what it looks like. So you have a photoreceptor at the top. Its output is going into a transconductance amplifier. And that forms a horizontal cell, right? Because now you just wire together all these transconductance amplifiers. You put a capacitor there to give it a time constant, make it lag behind. Then you take the output of the photoreceptor and its horizontal cell, and you wire it up to this bump circuit, flip it over so it's putting out current from the P side, and feed each of those currents into a spiking neuron circuit. And there you have one channel of your 3-layer retina. Is it clear? Yes, thank you, Hector. You were right. Eve's also got it right. Okay, so the question is, why are there no amacrine cells? Yeah, that's because amacrine cells are really complicated. Like I say, there's about at least 20 or 30 or 40 or 50 classes of amacrine cells. They extend over a big extent. Some of them are direction selective. It's not clear. We could have included something like that, but the functionality was not so clear. It's not just taking a difference, a high pass difference. It's hard. And only a couple of people have built silicon retinas with amacrine cell models on them. And the functionality provided by those amacrine cells was never very clear. And they occupy more real estate, right? Any time you put more stuff on the focal plane, you're going to get less fill factor, less area sensitive to the light. So that's still a bit open, what you might use it for. So you guys who watch the slide can just watch this video, or should I'm going to stop here for a sec. I have to share the screen with the sound. Actually, I think I will play it because the demo is kind of cool. You can see what I looked like about 15 years ago too. To share the screen with the sound. Tell me if you can hear this.
This is a demonstration of the off-type ganglion cell. Remove the stimulus around here. The chip here, the chip is looking up at this tangent screen. You can see here how it responds to this off stimulus, but not to a light field.
That's very short. Basically, what I was showing, I don't know if you guys saw it there, but you can watch it yourselves. What I was showing is that because this was one of the off-center cells, it needs a small off spot to make a response. If you make a big off spot, what happens? If you just make the whole thing black, what happens? Why does it not respond then? Let's go back to the previous slide.
Because the horizontal cells sum up to negative, like the average is negative, is nothing.
Yeah, that's right. So if you make everything black, then all the photoreceptors go down. That's true. Since they all go down, the average goes down too, and so there's no difference. So you need to be darker than your neighbors. That's the cool thing. So it does this, you have an off output and an on output. it's just like the dynamic vision sensor, event camera, right? Response to this contrast. In this case, it's spatial temporal contrast because of the averaging of the horizontal cell in space and time. All right, so I hope that's kind of cool to see how simple that some of these circuits can really be, and that you have, measured now with your own hands, most of them. I think I'll skip talking about the biological photoreceptor, the biochemistry of it, just except to say that it's very fascinating distributed biochemical amplifier. It's like a 3 or 4 stage biochemical amplifier that's all happening right here in these outer segments. And you can read about it in a lot of places. I highly recommend, if you're interested in this kind of stuff, there's a beautiful book by this guy named Bob Roddick. Bob Roddick's a very famous retinal physiologist who I got to meet at a retina course on Friday Harbor in Seattle, one of these islands that's out in the bay in Seattle, at a summer course. And he was just a really cool guy. He's dead now, but he wrote this beautiful book called The First Steps of Seeing. You see this picture here? I just showed it to you, the horizontal cells. This is absolutely a labor of love. And if you can find it, it's just a pleasure to read. I mean, it's like a life's work for him. So I highly recommend this if you want to read more about the biology of the retina. But I'll just say that what we try to capture in the electronic photoreceptors, exactly, for many years, we tried to capture this adaptation property, right? You get a low gain for DC and a high gain for AC. In other words, you should amplify the changes, which are presumably more interesting than just the static, boring stuff that's sticking around. It's a general principle of the nervous system extending from the sensory input on every sensory input all the way through the computation that's happening in synapses, in cortex. And so you guys know this circuit, right? That's the one you've been testing, this transimpedance logarithmic photoresensor with a feedback loop. Now this slide here, which is provided to you, it does some of the computation, and it explains why this photodiode has a large capacitance and a small photocurrent takes a long time to change this VS here. But this high gain feedback loop here clamps this VS at a virtual ground, and it speeds up the response. And the output voltage Vout is also the gate of this feedback transistor M1. So that kind of has a static gain. The gain is the same whether the signal is changing, or the DC gain is the same as the AC gain, kind of. It doesn't amplify more for changing signals than for DC signals. And so the way you make it adaptive to give it more gain is by reducing the gain. The general principle of feedback is if you want more gain, feedback less, and that forces the output to go more. And you can think about this adaptive photoreceptor with this capacitive feedback, which has less gain at high frequency than at low frequency, in the context of a feedback system like this, where the input is X, it's summed together with some feedback, which is the product of the output times B, and then feed forward, you have a high gain A. So you can analyze the whole circuit in this feedback system way. We're not going to do the adaptive photoreceptor, but I just want to tell you about some useful components that are in this adaptive photoreceptor, in particular this resistor. So the problem is, how do you make a resistor? In CMOS, you can make resistors out of polysilicon or N-well or something like that, but they tend to be rather small resistances. In other words, it's difficult to get a very high impedance conductive element. If you can get them, but they just occupy lots and lots of area. So how can you make a high resistance element using transistors? And why do you need a high resistance? Because you need a long time constant. You can get a long time constant by putting a big capacitor, but then that occupies lots of area. It'd be much better if you could just make a very small conductance. So how can you make a high resistance here? So that the time constant for this adaptation is long. And there's a cool trick that we came up with about more than 20 years ago now, how to make a very high resistance pseudo resistor out of one single transistor. And so if you do that, you can get these nice adaptive photoreceptor responses like I'm showing you here. I won't show you that stuff here. I just want to tell you about these pseudo resistors, these adaptive elements. So here's the trick. You take a single PFET, and now you want a resistance between VO and VF. And suppose you take a single PFET and wire it up like this so that the gate is hooked to the floating node and the source is hooked to the bulk of the PFET. Normally, this bulk would be tied to VDD, right? But what happens if you tie the bulk to this V0? Then you have a very interesting device, which in one direction, when VO is bigger than VF, acts like a diode-connected PFET. You can see it here, right? Imagine that VO is VDD. And turn this thing on its side, and then you have exactly a diode-connected PFET. And it has like kind of an exponential response, right? But now imagine that VO is less than VF. What happens then? Normally, you shouldn't do that because the N well always has to be higher than the P source drains. In other words, you don't want to normally forward bias this PN junction. But if you forward bias the PN junction, then you have a diode in the other direction, actually a bulk diode. Do you see that? So in one direction, you have something, a transistor that's diode connected, and the other direction, you have a physical PN junction that's forward biased. And if you do that, you can get an expansive pseudo resistor with a current voltage characteristic that looks like this. Here is the voltage across the element, or this is plus is when this voltage is higher than this one. So you see what happens here. In this positive direction, you get this diode-connected MOSFET that looks like this. And the negative direction, you get this PN junction. It looks like this. They're both exponential. They have different exponential factors. But the main important thing is that it's extremely flat here, and the current is very small for a big voltage range. And so that's why it's called a kind of like a pseudo resistor. It just has a resistor-like character. It's a conductive element, but it's very nonlinear. And so it can act like a kind of a very high resistance for small voltages and a low resistance for big voltages. And so this particular circuit element has been used in a lot of, since then it's been used in a lot of bioamplifiers, which are like the circuits, CMOS circuits that you put into brain implants to measure the electric potentials in the brain. So keep it in mind if you're looking, this is one type of pseudo resistor that you can build in CMOS that can give you a high resistance in a small area. Okay, so here is the pseudo resistor, right? It's a PFET. And like I say, you've got the capacitor over here. You can see this, right?
Yeah.
And here is the node you're actually driving. You're driving this by the amplifier. Here's what's we call the floating node, what I call VF there, and here's VO. And what we have to do is now tie the bulk to this side. That's what we call a pseudo resistor, where we had this this kind of an exponential IV relationship. Let's see, let's draw it like this. This is I going this way versus VO minus VF. It's exponential in both directions. In one direction, is it clear? So take this thing, take this circuit here and lay it on its side so that VO is bigger than VF. We'll just draw the voltage like this. Then what you have is now it's clear it's like a diode-connected PFET, right? If I put a VDD here, it'd be exactly a diode-connected PFET. That's clear, right?
Mm-hmm.
And then you have this exponential IV because then the I is equal to E to the kappa V. Let's say that VO is VDD. It's just delta V, kappa V times 1 minus E to the minus V. That's the drain. And then if V is bigger than a few UT, I equals E to the kappa V. I mean, I'm using dimensionless units. Because E to the minus V goes to 0. Right? If V equals 0, then the current is 0. I mean, that's clear, right? Because the drain source voltage is 0. But as soon as V gets more than a few UT, the transistor saturates and it just gets dominated by this gate source voltage that becomes e to the capital V. That's a diode. That's the equation of a diode when forward bias. So that's when VO is bigger than VF. But now when VF is bigger than VO, you can't draw a transistor anymore. Instead, you think about this, the fact that this is a P to N junction here. Yeah, that's right. It's a P to N because this is N well. You actually have that junction there. And now you have this diode like this, like a physical PN junction. And so in the other direction, when VF is bigger than VO, you actually literally have a PN junction, which is the source to well junction. This is the source, and this is the N well. And so that's also a diode.
Okay, thank you very much.
You actually do have, yeah, it's a little more complicated than that because you have a vertical bipolar transistor. You can look in the slide and you'll see that it's actually what they call a vertical bipolar transistor. If you look at the structure, you have a P, N, and P. So it's a PNP vertical bipolar. And so when you turn on this PN junction here, this one, you're actually turning on the base emitter junction, and the P substrate is a collector. There's one collector here, which is the other P source drain, and the other collector is the substrate. Whether you have a bipolar effect there or not is not so clear to me. A bipolar gain mechanism. But the main thing is just a forward bias junction. Now, the cool thing about this structure is if you put metal over it, if you actually shield it with metal, then it's very impervious to the effect of parasitic photocurrent. Think about it. I'm going to put a metal shield over this. This doesn't matter for a bioamplifier, but if you're shining light on the chip, it matters a lot. Here you have your gate. And normally what happens if you make a switch or something out of an NFET, suppose we put an NFET switch here instead of a PFET. And even if you cover it with metal, if there's an opening in the metal somewhere nearby, then this NFET acts like a photodiode. And it's very difficult to keep it from soaking up electrons and acting and leaking. But this structure here, this one, you can, if you cover it with metal so that no light shines directly on it, this junction here won't get affected by parasitic photocurrent because it's surrounded by that N well. And so you can blast light onto this thing, onto the surroundings, like on a surrounding photodiode, and it won't affect the resistance of this switch. It's certainly not true from any switch that you make out of a normal NFET. If you include an NFET, like it's tempting to try to make a switch like this. You do that in one direction, and you do something like this. You try to make an NFET in the other direction. Like something like that. That doesn't work at all, at least for a photo circuit. Because now when you shine light on this thing, it'll completely screw up this device here. It'll leak like crazy. Okay.
Thank you.
Sure, no problem. Okay, so I think I'm going to start with the so-called cascode. And it's it's called a cascode because I don't know why it's called a cascode. It's called a cascode because of the days of tube electronics. Because this particular shield in between the plates of in a vacuum tube device was called a cascode. I don't know why somebody came up with that name long time ago. But as I said, it's kind of a shield. I'll explain why it's a bit of a shield and how it deals with the Miller effect. Last time I talked about this Miller effect, and I'm going to draw here to explain the concept one more time. So the input stage of that amplifier that's feeding back in the photoreceptor in any feedback circuit looks like this, right? You have an NFET on the bottom, and then you have some kind of current source at the top. And I explained the Miller effect was this parasitic capacitor that was sitting right here between the drain of this transistor. And the problem with this Miller cap, the CM, is that it's amplified by the gain of this amplifier, which has a gain of, say, -A. So the effect of the CM is actually not CM with respect to the input node, which has to charge up this V1 here. It has to charge up not only the gate capacitance, which is to ground, but it has to charge up CM times A capacitance to the output. Because when this voltage goes down a little bit, the output voltage goes up A times as much. And so the effect is that voltage across the capacitor changes A times more than it did before. And so for the input node to charge V1 to a particular voltage, it has to supply that much more charge. So is that clear? So I told you last time that in the context of this photoreceptor, that if you increase the gain of this A, that speeds up the photoreceptor, but it only does it to a limited extent, the amount that it can cancel this parasitic capacitance to ground here, the C1. But it doesn't do anything about the CM, right? So if you increase A more, it increases the Miller effect more. That's why it's called CM, by the way. And so you don't get any speed up. And so what can you do about that? You got to get rid of that Miller cap somehow. And also it's beneficial to have lots of gain, but you have a basic trade-off between gain, high output resistance, and high transconductance, because you can get high output resistance by making M1 long. So if you want high RO, you make the L longer, right? If you increase the length of the transistor, you can increase the output resistance, but the transconductance of the device is kind of goes down as you make the device longer, in some sense. You can make it longer, but it's tough. So there's a trick called the cascode. How many people know about this cascode so far? Has anybody heard of it? I'm sure people that study circuit stuff know about this a lot. Hold on just a sec here. Let me show the participant list so you guys can vote. Okay, so one person heard of it and other people haven't. Okay, so here's the trick. It's a really cool trick. What you do is you put another transistor right above the first one, like this. And that has a very cool effect. I won't even draw this current source. I'll just draw these two transistors. So here's your input transistor. Let's call this M1 and M2. And here's your output voltage of your amplifier. Here's your input voltage. We don't care what it is right now. Well, let's make this V1. And VO stands for output. Okay, so let's see what that does. So what does that do to the output resistance from the viewpoint of VO? If I just put a voltage, a fixed voltage here called a VC, say 1 volt. So I'll put this here to like say 0.5 volts, that's subthreshold. And I'll put VC here to maybe 1 volt. Okay, so where does that leave this node Vx? What's the approximate value of Vx? Okay, so I know that the same current is flowing through the same transistor. So this gate source voltage is a 0.5 volt. And so since the same current is flowing through the top one, this voltage must be 0.5 volt. So Vx must be about 0.5 volt. That's enough to keep M1 in saturation. As long as M1 is in saturation, it's going to have a high drain resistance. So what's the drain resistance looking into VO compared to the original drain resistance looking into M1 on the left circuit? Is it doubled or more? What do you think?
Multiplied by the GM of the cascode transistor.
I couldn't understand the words.
So it gets amplified by the transconductance of the cascode.
Exactly. That's exactly the point. This is a very cool trick because this top transistor here kind of shields it like a waterfall. It kind of shields the drain of the bottom transistor. It increases the apparent drain resistance looking into VO by the gain, the intrinsic voltage gain of the top transistor. And I'm going to calculate that for you now so you can see the calculation one time. But the intuition that it kind of shields it. And so now the drain of this bottom transistor moves a lot less than it did before. And that increases, since it moves a lot less when you move VO, it increases the apparent drain resistance by a huge factor, say a factor of 100, quite easily. So let's do the calculation. So what we want is, I'll just do it in white here. So let's say that I is a small signal current, right? So we want I to calculate I. What's the small signal current I? That's the change in the current I. That's equal to GO times VO. GO is what we want to calculate. That's the apparent output resistance. But it's also equal to GD1, that's the drain resistance of the bottom transistor times Vx. And it's also equal to the current across the top transistor. So we got to calculate Vx. We don't know what it is. What's the current through the top transistor? Well, it's GD2, that's the drain resistance of the top transistor, times VO minus Vx. So that's the drain conductance. Now we have to include the source conductance because when VO goes up, Vx also goes up. And since Vx goes up, it decreases the current in the top transistor. That's the magic recipe. So you have to subtract GS2, the top transistor, times Vx. Is that clear?
Maybe I'm a bit confused with this because if we set the current from the top and we set the gate of the cascode transistor, the Vx should be sort of clamped to a certain value, right?
We're not really setting the current. We're asking if we change VO, how much does I change? And so what we're saying by definition, it's equal to GO, which is the GO that we want, times VO. So GO is what we're trying to calculate. And then we say that change in the current is equal to the change in the bottom current, and it's also equal to the change in the top current. Both of those currents are changing by the same amount, right? There's no other place for the current to go. That's what I'm doing here. Is it clear?
Yeah.
Okay. So now I'm going to make an approximation. I'm going to say that Vx hardly moves compared to VO. I know that already. So just to make it simpler, I'll just cross out Vx here. Basically, Vx is almost zero compared to VO, right? So I'll just say this is zero. That makes it a little bit easier. So now we got to calculate Vx, right? And substitute it in here because we want GO. Well, so Vx is equal to well, let's see now. How did I do this before? Oh yeah, so I can just put it together, right? Maybe I don't need to do this, what I just did. Let's just calculate it explicitly. So Vx times GD1, I'll move the GS1 over, plus GS2 as the Vx side equals GD2 times, I mean, I can really leave it out, right? Well, I'll put it over there too. GS2 plus GD2 equals VO GD2. Okay. Okay, so now, is that correct? I moved all the Vx terms over to the left. That's correct. Okay. Okay, so now I know that the drain conductance is going to be much less than the source conductance. So I'm basically just going to cross out these guys. Okay, so Vx equals VO D2 over GS2. I hope I did that right. And so then I over VO equals GO. Let's take this from this equation here. I divided by, let's see, I think there's something wrong here. Sorry, guys. Now I can get rid of Vx here. This is the right place to do it. Let's take this equation here. I say that I equals GD1 times Vx, which is GD2 divided by GS2 times VO. And so now I have I divided by VO, which is GO. Equals this expression on the right here. Okay, this is all kind of abstract here, right? But do you see how it's the product of GD1 times the ratio, or it's actually divided by GS2 divided by GD2? What's that? Isn't that just the intrinsic voltage gain? It's the ratio of the source conductance to the drain conductance. So let's be explicit here. Let's do it in subthreshold. It's GD1 divided by GS2 divided by GD2. And if we do it in subthreshold, I'll just leave the GD1 as it is. What's the ratio of source conductance to drain conductance in subthreshold? Well, remember, it's just the ratio of the early voltage to the thermal voltage, right? Isn't it? Do you remember that? Is that clear to everybody?
Yes.
Okay. Okay, so the output conductance is actually the original output conductance, but divided by this huge ratios. For example, this will be like 1/40th of a volt, and this will be like, say, 5 volts to be conservative even. So it'll be 5 times 40 times smaller. 5 times 40 is 200. So it'll be like GD1, it's the original drain conductance divided by 200. Is that right? 5 times 40 is 200? No, 5 times 4 is, yeah, 200. Yeah. It's cool, huh? So that's a nice trick. Anytime you want a high voltage gain stage, you put in a cascode like that. That'll get rid of the Miller cap and it'll increase the drain conductance a lot. Generally, you don't put a, it takes away a little bit of headroom, right? Because now this gate here, this gate has to be adjusted to hold the drain of the M1 transistor just in saturation. So you need some independent thing that will generate that cascode voltage for you. You have to hold the drain in saturation like a couple hundred millivolts or so. And it takes away a little bit of headroom. And so you generally don't bother with it for the PFET that's sitting on the top here, because you can afford to make that PFET really, really long. And so you just put a long PFET up there and then 2 short wide NFETs down here that together make a high output resistance and a high transconductance. So if you make them wide and short, they can have a big W over L and you can get a big transconductance for the same current. I mean, when you go above threshold. In subthreshold, the transconductance only depends on the current. But you can afford to make them wide so that they stay in subthreshold longer. Yeah, bigger current. And so this is a nice sweet spot, right? this is a really nice, this whole circuit here is just a really nice amplifier stage in subthreshold because of this combination of effects. We use it all over the place. Okay, so that's the first thing I wanted to tell you about. Now I want to go back to this feedback photoreceptor circuit and do some small signal analysis, continue where we were before. So let's draw that circuit again quickly. And you remember how it goes, right? There's a feedback NFET. That's some stupid thing here in my way. Okay. And then there's an amplifier here, the current source. Okay, and you guys did the calculation of this dynamics, as part of the exercise. You have an M1, M2, IB, and then you had a C1 and C2 sitting on the output like a parasitic C2. Both of those are parasitic capacitors, right? They're not intentional capacitors usually. And last time we calculated the transfer function of this thing, small signal transfer function, was that this is V1, V2, this is IP, which is some background current plus some small signal current. We said that V2 was equal to I over IP. So that's like the fractional change in the photocurrent times, what was it up here? Wasn't it a UT over kappa? And then in the bottom, we had this expression for the transfer function that was like tau 1, tau 2, S squared plus tau 1 plus tau 2 S plus 1, only there was a kappa A here, right? Where A was the gain of this amplifier. The gain here is minus A, which is it's the early voltage of M2 over the yeah, so it was something like that. Does this look familiar from last time? Do you remember how we calculated that transfer function? We basically just wrote down the small signal equations and then solved for the V2 as a function of the small signal input current. And what is tau 1 and tau 2? Tau 1 is the time constant of the input node, which is C1 over the conductance of the input node, which is equal to C1 divided by the conductance looking into M1, right? That's the dominant conductance there. There's no other conductance. You don't care about the conductance looking into the photodiode because it's a really small conductance, acts like a constant current. So the C1 was, what was the conductance looking into the source of M1? Somebody can tell me that in subthreshold. Right, in subthreshold, conductance is the current divided by the thermal voltage. So this is the photocurrent over the thermal voltage. So that's the input time constant. And then there's an output time constant too, which is the conductance, the time constant on the V2 node. And tau 2 was C2 divided by what? G out. It's the output conductance of this amplifier. G out 2, which was C2, which is C2 divided by, okay, so what's the output conductance? Approximately? Of M2. What was that again? The output conductance looking into M2. That's what we care about. Remember, it's an early effect, right? Not a transconductance, it's an output conductance. So basically, the output conductance of M2 is the bias current divided by the early voltage of transistor 2. Okay, so now you have explicit values for the time constants as a function of the currents and voltages, right? There's nothing abstract here. It's all concrete. If you know what the photocurrent is, you know what the bias current is, you know the capacitance, then you know these time constants. So now you have the whole transfer functions. You can plot it numerically and all that. What I want to talk about now is to tell you about a very cool concept called canonical small signal analysis for second order system. And I'm going to do that on another slide. And this is something that Carver did in his book, and I found it just incredibly useful over, the decades. Canonical second order system. All right. So what do I mean by canonical? So here we have a I hope it saved the whiteboard. Yeah. So here we have a second order system. It's a transfer function that has in the denominator an s squared, an s, and a constant. That's why it's second order, right? It's like two time constants. That's why you get the s squared. And so we're interested in a general form of this, right? When you have this quadratic in the denominator, it turns out that it's useful, although maybe not obvious to you right now, that you can write this h as, I don't know what happened to my canonical. You can write this h as 1 over, I'm going to just abstract it now. It's tau squared s squared. It's a different tau now. Plus tau over something called q, which will stand for quality factor, s, plus 1. So that's a very general form that you can put any quadratic into, right? You just have to call the factor in front of the s squared tau squared and call the factor in front of s tau over q, and then you can calculate tau and q, okay? In particular, for our circuit, here we have tau squared equals tau 1, tau 2 over kappa A, right? I think that's how it came out. And tau over q was equal to tau 1 plus tau 2 over kappa A, something like that. Okay, now why am I showing you this? This is quite abstract right now. The reason is I want you to think about this expression on the left here in terms of this q. So tau is going to be somehow a time, right? Because it's multiplied by the frequency. So time times frequency is dimensionless on the left here. So tau is some kind of generic time constant. Q is some measure of how important this middle term is. So what happens if Q is really, really big? Okay, if Q to infinity, then what you'll have on the bottom is that tau squared, if you want to find the poles, the roots of this bottom thing, then tau squared s squared plus 1 equals 0. Okay, so what s can solve that? In other words, what s can make that true, that tau squared s squared plus 1 equals 0? I mean, a positive thing plus positive thing equals 0, right? So the first thing must be negative. How can you get a negative number at the first term? S has to be imaginary, right? Has to be a complex imaginary number. So S in this form, S must be plus or minus J over tau. If Q gets really, really big, it just describes something where the solutions are just on the imaginary axis. I'm going to draw that over here on the S plane, where this is the imaginary, this is the real. So if Q gets really, really big, then the solutions are going to be appearing like right around here, very close to the imaginary axis. All right, it's Q approaching infinity. Okay, now the solution for Q approaching 0 is a little bit hard to understand, but what if, I'm just going to take the limits here. What if Q is equal to 1/2? Okay, so then on the bottom, we have this expression, tau squared, s squared, plus 2 tau, plus 1 equals 0. What's the solution to that? What s, 2 tau s plus 1? What's this, what s solves that? This is kind of cool, actually. Q equals 1/2. Then you'll notice that this is a perfect square, right? This is tau s plus 1 squared equals 0. So now what s solves that? S equals minus 1 over tau, right? S equals minus 1 over tau. So when Q approaches 1/2, and you'll see that as Q gets smaller and smaller, this typically will trace out a curve like this. So trace out a curve like this. Why can't I draw here? For some reason I can't draw on top of that symbol. As Q approaches 1/2, these poles start to approach the real axis, and they approach minus 1/2. They approach minus 1 over tau. And this is j over minus j over tau. Okay, and when the poles start to approach the real axis, you just get a pure exponential decay. Remember a long time ago that I said that s is the factor in front of e to the st, right? You have e to the st is the time domain solution. And if s is imaginary, then you get these sinusoids. But if s is real and negative, then you get an exponential decay. Right, so that kind of describes how stable it is. So what this shows is that when Q is really big, like it's a kind of a very ringy response. But when Q is small, it gets like to 1/2, it becomes more like an exponential response. And so it kind of describes how stable the response is to a disturbance. Because remember, this is the natural response. If you kick the system, like capacitively coupled to it and kick it, how it responds. Does it come back like a pure exponential? Does it ring a bunch of times? And it turns out that Q is a quality factor, is approximately the number of cycles of ringing. So if you can extract Q from your transfer function, then you can basically say how stable the system is. Right? Is it going to ring, or is it just going to like nicely approach the final value? All right, so now we can take the actual photoreceptor transfer function and figure out what tau and Q are from it in terms of tau 1, tau 2, and A and all that kind of stuff. And we can make some interesting observations from that. But first, before I go on with that, it's quite a bit of algebra to figure that out. And there's some shortcuts you got to take to make it simple. But just ask if there's any questions.
Okay, so might sound a bit silly, but what do we mean by ringing?
Ringing means the number, if I kick it, let me go back to the circuit. What the hell does this mean? This Microsoft whiteboard is pretty nice, especially with a pressure tablet, but it's kind of buggy with the network. You're supposed to be able to share these whiteboards with other people and scribble at the same time, only it doesn't actually work, unless you have a real Microsoft account on some business plan. But it's all right for drawing on. Yeah, so it just means that if I were to couple into this circuit at this point with a square wave, and then I look at the output here, does it respond? Does it come back like this, nice and exponential? Or does it come back with, in case of a high Q, instead of coming back like that, it would go back like this.
Okay.
right? Be unstable, be marginally unstable. It kind of represents the unstableness of this second order system. So Q is like, think of it like a clock or a pendulum. You know, you want a high Q. If you have a crystal with a very high Q, like a crystal oscillator, that means it's a high quality crystal. Just keep like it's like a high quality bell. Keep ringing for a long time. Usually you may want that if you have an oscillator. You may not want a high Q if you really want to guarantee stability. Okay.
Thank you.
Okay. So what I'm saying is that you can now take any system and look at it in terms of this canonical second order system. And if you can figure out what the tau is and the Q is from your expression, then you get a good intuition about the dynamics and stability of this system. And I'm going to do that now for this photoreceptor circuit, and you're probably in your future career as an electrical engineer, you'll do it for something else like some audio bandpass filter or something like that. All right, so let's actually do that. That's a little bit complicated because of the algebra. I hope I got all the actual equations correct. I better just check that I got that correct.
Okay, I have a question. So
I think I got it right.
So I have a question. So the quality factor is generally dimensionless, right? Or unitless?
It's dimensionless, yeah, because the tau already has the dimensions of time. So tau S is dimensionless because tau S is frequency, right? Tau is time, so this cancels out. So Q is dimensionless number.
This definition that you mentioned about the number of cycles per, I think I missed that part. Just
yeah, that's a good point. I say that. Yeah, it's because the Q describes the nature, how close to the imaginary axis the roots of this polynomial are. So if Q approaches infinity, like I said, the middle term of this polynomial goes to 0, right? I don't know if you see my mouse here. The middle term, yeah, the mouse, yeah. Can you see my mouse?
yes.
Yeah, so the middle term goes to 0. As I said, if the middle term of this quadratic goes to 0, then S must be an imaginary solution, because otherwise there's no way that tau squared S squared plus 1 can equal 0. You have to have S be imaginary. It can't be real, right?
Yeah.
Because if you square a real, it'll be positive. You can't add positive to positive. So you have to get this negative. The only way to get it negative is if S is imaginary. And if S is imaginary and it's close to this axis, that means that your solution, e to the st, will be dominated by not the real part, which is a decaying exponential, but by the imaginary part, which is a sine and cosine. That's why it's ringy. If it's dominated, if S is dominated by the real part, which is negative, then it's dominated by a negative decaying exponential.
Okay.
Okay. Thank you. Okay, so let me now attempt to do this for the actual photoreceptor circuit in terms of this canonical analysis. Canonical means like supposed to be generic analysis. So just by memory, I'm going to, like the wizard, I crammed all this stuff into my brain this morning. Tau squared in this canonical form is equal to tau 1, tau 2 from our photoreceptor circuit, and tau over Q, tau 1, tau 2 over kappa A. That's the loop gain. Remember, kappa A is the gain all the way around the loop. You get the A from the amplifier and the kappa from the source follower feedback. They're going through the gate. And tau over Q is tau 1 plus tau 2 divided by kappa A. So now we can solve for tau. It's exactly just the square root of this product of the two time constants divided by the loop gain. And we can also solve for Q. Q equals a tau, which is square root tau 1, tau 2 over kappa A divided by tau 1 plus tau 2 over kappa A. Did I do that right? Q is equal to tau divided by that, and tau is equal to that square root. There's a square root around the whole thing. Okay, it's like this. Somebody please tell me if I'm wrong. So now I can write this out. It's actually cool because now it's all inside a big square root. It's tau 1, tau 2, tau 1 plus tau 2 squared. And when I put the kappa A inside the square root, becomes on the top, right? Yeah, it becomes kappa A squared. So it's kappa A like this. Okay. So let's ask the question now in this circuit. This is the only question I'm going to ask here. In this circuit, given a particular photocurrent IP, what IB do I need here to make this response stable? So remember let me go back a bit. Remember in the beginning, I showed you by looking at this transfer function that if we made tau 2 equal to 0, in other words, if we made this amplifier here infinitely fast, then we got this speed up of kappa A. Do you remember that? Because then that increased the source conductance looking into M1. If you make tau 2 infinitely fast. Okay. So the question is how fast do you actually have to make tau 2 in order that you get this ideal response, that it really has that effect? Because you don't want to burn infinite current in IB, right? So you can answer the question now by asking what IB needs to be. In other words, what does tau 2 need to be to get Q equals 1/2? In other words, to get the response to be a nice exponential response to the output instead of ringing. So let's do that. So the way you do that is you want to ask the question now, we want this to be a half, right? This is probably a bit abstract for you guys, but anyway, so let's say 1/2 equals this thing here. So that means 1/4 equals tau 1, tau 2 over tau 1 plus tau 2 times kappa A. Okay, now I'm going to make an approximation, and this is the trick to make it solvable easily, is just to say that I already know that tau 2 is going to be much less than tau 2 is going to be much, much less than tau 1 for this to be true. I know I have to make the amplifier fast, right? So I could just cancel this here, this part. And then that allows me to cancel out tau 1 as well, because now it just cancels. So now I know that tau 2 was equal to 1/4 kappa A. So in other words, the time constant of the output node has to be faster than the time constant of the input node by at least the loop gain, 4 times the loop gain. So it has to be really fast. Like suppose the loop gain is 100 going around. That means the amplifier has to be 400 times faster than the input time constant. That's a lot faster, right? And the higher you make the gain of the amplifier, the more it has to be faster. So that's one interesting thing you can observe. And if you do that, though, you should get a stable response to the final value. No ringing.
Excuse me, wasn't the denominator squared? Like tau 1 plus tau 2 squared?
Oh, you're right. Thank you. Thank you for catching that. I knew there was something funny about my solution. Okay, so this is actually squared, right? But we can still cancel tau 2, right? Oh yeah, you're right. The dimensions, the units don't even work out. Thank you. Okay, so it's actually turns out to be, let me rewrite it here. Yeah, thank you for catching that. By the way, if you notice on the uploaded video last week, I made a couple of mistakes, but I put in some little cartoon bullets to show that I had made those mistakes into the final video. Okay, so it's actually squared, right? Okay, so let's say the tau 2 is much less than tau 1, so we can cancel it out. And now we have a 1 over tau 1 here. And so tau 2 is tau 1 divided by 4 kappa A. Okay, so it has to be, faster than the input time constant by 4, times the loop gain in order to get a stable response. So that's one question. So that answer to the question is how much smaller does tau 2, how fast do you have to run the amplifier to get a stable response? What's the other question you can ask? The other question you can ask is how much can it ring if you make the time constants be the same? And it's natural to ask what happens if tau 1 equals tau 2? What's Q then? So this is stable, make it stable. And by the way, this tau 1 changes. As you change the photocurrent, tau 1 changes proportional. I mean, this tau 1 is proportional to 1 over the photocurrent, right? So the brighter you make the light, the more current, ideally, you have to run in that amplifier to make sure it's stable. Okay. What's the maximum Q? That's the other thing I'm going to try to answer. What's the maximum Q value? Well, Q is equal to this expression on the top right here, right? So I'll just tell you that the maximum Q is when tau 1 is equal to tau 2. You can get it by differentiating the thing and setting it to 0. But I'm pretty sure it's when tau 1 equals tau 2. And then what you find out is that Q is true that when tau 1 equals tau 2. And when that's true, then Q is equal to what? It's just tau squared. Basically, it's tau squared divided by a 2 tau times kappa A square root. Okay. It's equal to tau times the square root of the loop gain over A over 2. Okay. So let's just call this tau 1. Okay. So when you make the time constants on those two nodes the same, then you get a Q, which is proportional to the square root of the loop gain. Like if the loop gain is 100, then the Q would be 10. So it should ring roughly 10 cycles. Is that clear?
Professor, if the taus are the same, the denominator then is 4 tau squared, not 2 taus.
You get a tau squared on the top and a 2 tau on the bottom.
But to the power of 2. So 4
Did I make a mistake?
squared.
Oh yeah. Did I make him? No, this can't be correct, man. It must be dimensionless.
And that's why it's
it's squared. Yeah, it's squared. Yeah, thanks. Oh, stupid. Okay, it cancels out. It's not it's 4. It's 4 tau squared. Is that correct? Did I get that right now?
Yes.
Okay, so it's root. Yeah, it's approximately. Anyway, it'll ring roughly the square root of the loop gain cycles. So what I suggest you do in your exercise is to try to get that condition and see if it's really true in the transient simulation. So all this is just to give you some experience with this kind of second order analysis. If you have one of these transfer functions where you have a quadratic in the bottom of any form, you can always look at it like one of these canonical second order systems and think about the relative values in front of the S squared and the S. And you can think about it in terms of this Q kind of analysis and this tau. And it's really helpful to get insight on this kind of second order systems. And so now you have this notebook. I mean, you don't have to make this your life's work to look at it, but you know, you have a nice notebook that you can play with this stuff numerically. Since now it'll give you a lot of practice calculating the gains and stuff. And the beautiful thing about the simulation is everything is perfect. Everything is ideal. There's no cascade. There's no Miller effect. So when you put in an early voltage for the M1 transistor, you really get a voltage gain in the simulation, which is exactly the early voltage divided by the kappa times the thermal voltage. And so you should be able to see this kind of stuff quite easily. In reality, you're going to get some parasitics and stuff that kind of muddy the picture. So is this mystifying? Some people are completely mystified by this analysis. I could tell by your expressions here. But I think it's worthwhile if you're ever going to do some second order stuff. I found it like I've used this over and over and over again whenever I've analyzed different kinds of circuits over the years. I know it's not the conventional way to look at amplifiers where you do a Bode plot and you see when the phase gets to 180 and you make sure that the gain is less than 1 at that point. I never found that kind of analysis very useful. Although maybe the amplifier guys are smarter than me. I always like this better.